So what I want to do for the last part of the semester, as I've said, is the whole thing in focus?
Yes.
Okay. Is I want to talk about applications of probability in the real world. And so I have done a lot of work in the sabermetrics community. This is applying mathematics to baseball. You can, of course, apply this to other sports. What's better about baseball than any other sport?
There's no skill involved.
All right, Cameron, you can hit her. I can't, you can. She's the third girl behind you. Okay. Yes? I'm a little bit off. Okay.
It's easier to separate the outcomes.
It's easier to separate the outcomes. You know, in football, you have so many things ranging from the offensive line, do they hold, to how good is your defense, where do you start off with the ball, to do the officials know the rules, you know, so many different things. Sorry, Pats fan. Baseball, you have a lot of individual competitions, you know, pitcher, batter, and it makes it a lot easier to isolate the contributions. You also have a lot more data. The baseball season is 162 games. Football is 16. You know, basketball, hockey, intermediate at around 80. Okay, so what I want to do is I want to talk about some applications of basic probability and multivariable calculus to solving real-world problems in baseball. I have talked to general managers of major league teams. I've done a lot of work. I've been in some of the books. I can't say certain things while being recorded, but I am happy to have the conversations when the tape stops. Okay, so as always, I'd just like to say that this talk is dedicated to my great uncle Newt, who assured me when I was young that I would live long enough to see the Red Sox win a World Series championship. Okay, so this is now a tax-deductible trip to Boston because this is now business. This is us going to see a Red Sox game to gather some first-hand data. Oh, we forgot to bring Wally today. Wally's supposed to come whenever we give this talk.
Daddy,
Yes?
it's in your room.
I know, you gave me Wally back, I forgot. All right, so I want to talk to you about the Pythagorean one-loss theorem. How many of you have heard about the Pythagorean formula in baseball? Okay, only 1 or 2 hands are up. How many of you have ever looked at the expanded statistics on like ESPN or MLB? They often do predicted wins, losses. That's what the Pythagorean theorem is used for, is trying to predict how well a team will do. So the goal of the talk is I want to give a derivation of the Pythagorean one-loss formula. I want to give you some idea of why it's true. A lot of the people who work in this subject, and I don't want to say anything bad about the statisticians, is they analyze data, they look for patterns. But just because something is held for a while does not mean it's going to continue. You know, for example, we haven't had a pop quiz at all throughout the semester. So I want to talk about observing key ideas. And from those key ideas, what are the techniques we need to actually model? Modeling is extremely difficult because there's a lot of different things going on in the problem. What do you have to do as a modeler? There's so many things going on in the problem. What do you think you have to do as a modeler? Yes? Make assumptions. And you have to trim. You can't include everything. When Galileo dropped the 2 spheres off the Tower of Pisa, I think we talked about this, does it matter what color they were? Probably not. There could be a little bit of heat absorption difference as they're falling through, and maybe if one of them was hot because they've been sitting out in the sun for a couple of hours, maybe that makes a small difference, but for the most part it probably does not matter. And you want to trim your model to the key parameters that really matter. We're going to see how advanced theory enters even in very simple problems. There's also an enormous amount of opportunities from inefficiency. So there are 2 major career paths for Williams students. How many are planning on going into finance? Okay, so I guess the rest of you will be the consultants. So there's a huge amount of money you can make from inefficiencies. It doesn't just have to be inefficiencies in baseball. There are so many different things you can exploit. That's one of the goals of today's talk. And the last, some extra stuff, there's a lot of research projects here. So if anybody's interested in pursuing any of this stuff further, please let me know. Okay, so the goal is to find good statistics to describe the real world. Okay? There's a lot of different things you can keep track of. Anybody know any statistics from baseball? Yes? Batting average. So for a long time, batting average was considered a really good statistic, and now it's been supplanted by a bunch of other statistics. So I want to talk about the following. So this is Harvard Bridge. Anybody ever been on this bridge? Why is this bridge famous? Yes. So laws are very different now, and probably for good reason, as to what you are and are not allowed to do with college students. Back in the 50s and 60s, it was actually acceptable as a fraternity to pick up one of your pledges and lay him down on the bridge and mark off one unit, pick him up again, mark down another unit, pick him up again, mark down another unit, and just measure the entire bridge and see, I wonder how many smoots would fit in the bridge. And so the fraternity found out, I forget the exact number, and then what do you think the Cambridge police did? Erased it. So what do you think the fraternity did? Did it again. Hey, Smoot, we need you again. So this went on for a while, and at first the Smoot was not well received, but eventually the Cambridge police embraced the Smoot. And now when there are traffic accidents on the bridge, they actually give you the Smoot marker as to where the accident happened. And so Smoot has become epitomized as a wonderful statistic. Does anybody know whatever happened to Smoot? He will appear at the end of the story. He had a very interesting life. This is not a great statistic. Now, MIT is famous for having interesting statistics. Have you ever heard of the Bruno? What's the Bruno? It's the indentation, I think, in cubic centimeters made from dropping a grand piano off a third-floor building into the cement below. Again, not a great statistic. So we want to find good statistics. So, okay, I did write down. The Harvard Bridge was 364.1 spoots. I was originally going to give another talk today, just found out this morning with school canceled that I would shuffle things around a little bit. Plus or minus 1 year. All right, so the goal is to go from this. Who can recognize this? Yes, Kayla? That's your T-ball team. And when the camera's not recording out, and your coaches. I will talk to you about the T-ball team. One of the shirts is actually not green and has been computer edited. So as extra credit, see if you can figure out later which shirt was edited.
I know.
Yeah, I know you know. So shh. If you could get Kayla to tell you, which team is this? Kayla's Berkshire team. So which team is this?
The Williamson team last year.
I think this was 2 years ago.
No.
Oh, that was last year? Oh, okay, that's right, last year, this year. I've already moved on to the next baseball season as treasurer. So we want to get to championship status. To really championship status. Anybody know what I'm wearing? Be more specific. I love being able to say that. Yes?
From 2004?
Nope, 2007. So we were visiting one of my father's cousins in Maine, and we were chatting about the Red Sox game the night before, and he happened to casually mention about the first time the Red Sox sent him a ring. And I'm a mathematician, and I go, you can't say first time when it only happened once, but only mathematicians would speak like this. You don't say first unless there's a set. How many rings do you? He has 3 Red Sox World Series championship rings. He used to be chief of police at Tufts. He retired to Florida. He worked spring training for the Red Sox. They were extremely generous. I will not say, since the tape is recording, what I offered in exchange for this ring, but I still have a bunch of things as well. So, anybody know the basics of baseball? I'm sorry?
So
Somebody pitches.
So, and then you have a bat
You have a bat,
and you try to hit it.
and you try to hit it. And how do you tell if you win?
By how many runs.
Okay, so
And a run is where you go from home
mhm.
to home again. You can't just go on home and then jump.
Right.
You have to go to first, then
Yep.
second, then third, then home without being tagged
Excellent.
or get out.
And how do you tell which team wins the game? Yes.
How many runs?
Okay, be more specific.
Like
Which
if
has
you have
the most?
more.
Which has more? It's not like golf. Whichever has the most runs wins. Okay? Unlike golf. So we want a really simple formula. The key inputs are going to be the runs scored by the team. So RS is going to be the average runs scored per game. RA is the average runs allowed per game. And gamma is some parameter. It'll be different for baseball than basketball, than football, than hockey. And the Pythagorean one-loss formula, Bill James came up with this, I think, in the 70s, just from numerically looking at the data. And he found a really good approximation for a team's winning percentage is the number of wins divided by number of games is about runs scored to the gamma over runs scored to the gamma, runs allowed to the gamma. And he originally took gamma to be 2. Numerical studies have shown that the best value for gamma is about 1.82. Any idea why he took 2?
If you round it to the nearest part,
Well, he didn't know the best value.
it equals near 2.
Well, but why do you think he chose 2?
I don't know.
Not 2 teams. Well, he didn't want to have the pain of using a calculator. It's much easier to just square things. And so he used 2 because it was very simple to compute with 2. And it's not a huge improvement to go from 2 to 1.82. Why is this called the Pythagorean one-loss formula?
It's like one leg of a triangle over the hypotenuse.
Yeah, I mean, basically, it looks like Pythagoras' theorem. There are really not triangles in baseball unless you cut the diamond in half or you look in the outfield in Fenway Park. But it looked like the Pythagorean theorem, so he called it the Pythagorean one-loss formula. So you can actually put in different values and see how good of a job it does. So, in 2009, the Sox were 95 and 67, scored 872 times, allowed 736 for prediction of 93.4. So not bad. Now the Yankees were predicted to be 95 wins, but had 103 wins. So the question is, how accurate is the formula? And when it's not accurate, what does that mean? In 2011, there's a long story for the Sox fans, and I'll just leave it at that. So here are 3 uses for the Pythagorean formula. One is extrapolation. So partway through a season, you can see how a team is doing versus how you would predict them to be doing. And you can get a really good sense of, are you overperforming or underperforming? Who's your real threat in the league? If you're not having a good season, should you give up on the season and conserve your resources for next year? Or are you just having a string of bad luck? I remember a couple of years ago, the Yankees started off, I think like 21 and 29 in their first 50 games. As a Sox fan, I was really happy. But all the metrics said the Yankees were much better than their record indicated. And the Yankees, in fact, decided not to give up on the season. They made a play for Roger Clemens, and they got him. And they replaced their number 5 starter, their weakest starter, with Roger Clemens and made the playoffs. So being able to extrapolate is extremely important. Another is evaluation. So if you want to evaluate how good of a job a manager is doing, typically they use the Pythagorean formula to see how good of a job a manager is doing. If he consistently brings in more wins than expected, the belief is the manager is doing a good job. The last is the advantage. So this is a very simple, easy formula to use. It's nice in terms of the parameters. We don't have to resort to numerical simulations. We can just vary the runs scored. If we want to see what would happen if we made a play for this player who would increase our runs scored by 10, or we made a play for this pitcher who would decrease our runs allowed by 10. What? No. Okay. In the last 5 minutes you can come, okay? So is it better to decrease the number of runs you're allowing or to increase the number of runs you're scoring? The value of a player is not independent of the team. A really good player going to a really good team is not worth that much. The most value a player has is when they go to a team that is just below the threshold for making the playoffs and can push them into the playoffs, because that's worth a huge amount. The other ones are here. Okay, so you can keep doing predictions throughout the year. The number of wins can fluctuate greatly as teams go through streaks. And we'll see later that it's accurate typically to about 4 games per season. Okay, anybody know where this is from? This game show is in our textbook. Anybody? What? What game show is this from? This is from Price is Right. And this is essentially the central limit theorem. I can't seem to use my cursor. I don't know why, but here it is. All right. So there's a bunch of pegs, and every time the ball hits a peg, it's supposed to have a 50-50 chance of going left or right. So what should the distribution rate be if there were at least infinitely many pegs up here? What would you expect the distribution down here to be? A normal. And so if you start the ball very close to an edge, you're very likely to get some money, but not the big money, which is put over here in the middle, surrounded by 2 zeros. And so we want to do some basics of probability. Now, this part should be fast because this is a probability class. So the goal is to observe some kind of statistical distribution. Say we observe a scoring distribution like this, and we want to come up with a way to model it. So this is a joint class math and stats. I want to talk a little bit about the stats side of things today and how you use all the probability we've been doing. So standard review for us, if x is a random variable with density p of x, the density must be non-negative, it integrates to 1, and the probability you take on a value between a and b is the area under the curve. This is why I love why I love integration so much. It gives us probabilities. The two big concepts we need is the mean, or the average value, and the variance, how spread out things are. And then the notion of independence, if you have two random variables, they're independent if knowledge of one gives no knowledge of the other. So here are the guidelines for modeling. The model should capture the key features of the system, and it should be tractable. Anybody ever watch the old Charlie Brown baseball episodes? Okay, what happens to Charlie Brown when he plays baseball? Ball goes, cat falls off, his team is... It's horrible, horrible. He never has had a good baseball game. Things are always going bad. This is to illustrate the dichotomy between the two things. The more features you capture, the more accurate your model should be. But the less tractable it's going to be, the harder it's going to be to have something useful at the end of the day. So we need to do a very delicate balancing act. We want to include enough stuff so that we have a sense of what's going on, but not so much stuff that we can't get useful information at the end. So I'm going to propose a model, and I want everybody to try to pick holes in it. The runs scored and runs allowed are independent random variables, and they give them some nice density functions. So can somebody give me something that might be wrong about runs scored and runs allowed being independent? Yes?
Runs scored can't be more than runs allowed.
No, you could win by a lot.
So what is runs allowed?
Runs allowed is how many runs the other team gets. It's how many runs you give up. Yes?
I mean, if you score a really large amount of runs, you might be more likely to give up a run. And not really care about it.
Yes. Anybody know who Remlinger is? There's a reason. He didn't last long with the Red Sox. When he came in to pitch one day for the Red Sox, the Sox were up 10-3 in the 9th inning. And I still remember Fox Sports did not list his ERA. The ERA is the earned run average. It's how many runs you allow on average in every 9 innings of work. Anybody know why they did not list his earned run average? Nope, it was not his first game with the Red Sox. It was undefined. Why was it undefined? He had not gotten anybody out. He'd given up runs as a Red Sox, but he had never gotten anybody out yet as a Red Sox. His ERA was plus infinity. And they just didn't have the symbol for plus infinity. He proceeded to give up a grand slam fairly quickly, and he made a 10-3 lead tight, but he did get the 3 needed outs. So if you have a huge lead, you will definitely put in weaker pitches. What else might you do? Yeah, if it's clear you're going to lose, you might not put in good relief pitches. You might put in other people to give them practice. There's a lot of issues with something like this. There's a lot of holes with this argument. The idea, though, is it leads to a very simple model, and hopefully a lot of these things cancel out. Which would you like to model? Runs scored and runs allowed as continuous random variables or discrete? So if it's continuous, we would need to calculate, if we want the first group scalar, don't kick that. Is it still in focus? Thanks. So if we want to calculate the probability we win, we want to calculate, if x is the runs we score, then we look at all the values for the ones we allow up to x. And since it's an integral, we can do less than or equal to, because the probability that they're equal is a lower dimensional space. It has contribution 0. Or we could look at a sum over all I, where we score I runs, and then we allow j runs where j is less than I. Which would you rather do, an integral or a sum?
Get half a run, so the sum is like...
Yes, the Red Sox are never going to beat the Yankees by a score of pi to e. So from physical grounds, from realistic grounds, the sum is the way to go. Which way do you think I chose? Integral. Of course I chose integral. I wouldn't do sums. Why would I do integrals? Yes? You can use calculus, right? I've spent all this time going to school learning all this advanced math. I want to use it. You can have closed form expressions with calculus. So the real questions are runs scored and allowed independent random variables? And can the integral or sum be computed in closed form? Who knows who Bud Selig is? Former commissioner. But before he left, he changed baseball. He added a rule to make sure a terrible catastrophe which happened in an all-star game would never happen again. What was this horrendous event that he has made sure future Red Sox and baseball fans will never have to see? Tie games cannot happen in baseball. We do not have enough time to go into how bad it is for a baseball game to end in a tie. It's just catastrophic. It's just horrible. And Bud Selig made sure that this will never happen again. Baseball games cannot end in a tie. Do you think runs scored and runs allowed are independent? Why not? They can't be equal. So years ago, I was watching the game that's now known as the Mother's Day Miracle for the Red Sox. It was on Mother's Day. The Sox were playing the Baltimore Orioles. If you need a team to give you interesting statistics, the Baltimore Orioles often come through. The Orioles were leading 5-0 going into the bottom of the 9th inning. The Red Sox score 6 runs, the final out coming from an error. Maybe the final 2 runs came from a double error. And the Red Sox win. So if I tell you Baltimore scores 5 runs, you know the Sox can't score 6. I'm sorry, can't score 5. They might score 6, they might score 4, but you know it's not 5. So runs scored and runs allowed can't be independent. So this leads to some really good statistics as to how do you take into account the fact that they can't be equal in your modeling. And so I'm not going to go into too much detail with that, but I will give you some appendices if you want to see. For those of you who have done R by C contingency tables and stats, who's done an R by C? No one's done R by C contingency tables? Wow. All right, if you continue in stats, you'll see things like this, and you'll learn how to handle, by using stuff like this, the cases where you can't have equality. If a patient goes to a hospital for treatment, what would you like to assume? Yes?
They're okay.
Well, they're okay when?
After?
After. You'd like to assume the hospital makes them better. Does the hospital always make people better? No. But what would you at least like to assume? If we don't make them better, at least we don't make them worse. Sometimes they do make them worse. They sometimes operate on the wrong person, or on the wrong body part. Things like this happen. But for the most part, for a lot of things, you can assume that you're not going to make anybody worse. And that limits the possibilities of outcomes. And you have to have a statistical way of dealing with stuff like this. And in fact, what got me into the sabermetrics community is when I wrote my paper, I actually dealt with this issue. And the senior quant person from an MLB team saw this and wanted to talk to me about how you do this. I was actually visiting colleagues in Europe at the time. I have all my papers available on the web. So when he sent me the email, that same day I could send back, here's all the papers I used in my research, here are my notes. You want to be able to respond quickly and make good impressions. And this led to a wonderful connection between my students and this franchise for several years, including some very nice behind-the-scenes tours. All right, so here's my first proposed model for runs scored in a baseball game. It's the uniform distribution. It's a nice model. It's an easy function to work with. You need some knowledge of baseball to outlaw this. So what's wrong with this?
You're more likely to score 2 runs than 10 runs.
Yeah, not all scoring is equal. And in fact, you could score more than 10 runs. There's a wonderful game involving... Nope. I told you which team. Baltimore Orioles. So this also indicates one of the worst statistics in baseball. Anybody know one of the worst statistics? It's a pitching statistic.
Wins and losses.
Nope. Worse than wins and losses. Save. The save is one of the worst statistics in baseball. Anybody know the definition of a save in baseball?
It's when you come in and you're leading, you don't blow the lead
Got to be more specific.
by 3 runs or less.
By 3 runs or less, and you're the final pitcher. But there's an asterisk. There's another way to get the save. If you pitch the final 3 innings, no matter how much the lead is, you can get the save. So the Orioles were playing the Texas Rangers. The Texas Rangers were leading 14-3 after 6 innings. How much is 14 minus 3? 14 minus 3, 11. They brought in a relief pitcher. The final score was 30 for Texas, 3 for Baltimore. Texas scored 16 unanswered runs. Their relief pitcher pitched the final 3 innings and gets the save. My kid's great Grammy could almost hold that much of a lead. But it's called a save. So you can have high-scoring games, and this is also a great example of a statistic that is very bad but sounds good. When you hear the word save, you think somebody did a great job. Who's famous for being a really good general manager and knowing how to use these statistics? Billy Beane. And so one of the things he did is he took a lot of his relievers and he put them only in situations where they would rack up saves. They're like, oh, you want my star reliever? Oh, no, I can't be at a par with him, but I do need a second baseman, so all right, I'll make the trade. Now, of course, you can only do this so many times before people catch on, but you can do this for a while. And if people are valuing the wrong statistic too highly, you have a huge competitive advantage. And so he was wonderful at doing that. And he and the A's organization found that on-base percentage was actually much better predictor of success than batting average. And they helped shift the movement to that. And they knew that the save was a very bad statistic that a lot of people glorified over well. All right, if we don't do a uniform distribution, what's a good guess for next distribution? Easy one to work with mathematically, one of our favorite distributions. Normal. All right, let's see which one I do next. Thank God it's the normal. Why is the normal bad for baseball? So one thing is it allows negative runs. As bad as the Sox were this season, they will not score negative runs in a game. There's another issue with the normal. I'm sorry? Yeah, well, we've already said we're going to accept continuous. What's another issue with the normal? There's something about the normal that's not realistic for a baseball game. Be more specific about many runs.
You're not going to have a lot of the runs be like 5.
Well, I mean, we could make the normal fatter. So, I mean, it might not have the right shape, but this allows you to score a quadrillion runs in a game. Now, the probability of scoring a quadrillion runs is less than individual meteorites hitting each and every one of you while I chant, "Go Yankees, go Giants." Okay? It's extremely unlikely with the Gaussian that you would have that event happen. The probability is so small. And this is a really good mathematical technique to be aware of. It's much better to work with something that's mathematically tractable, even if it's a little bit unrealistic. We could do a lot of these integrations. Let's allow us to score a quadrillion runs. The probability is so small that effectively we don't have to worry about it, but it gives us a nice continuous distribution to work with. Yes? Is there a mercy rule? No. When in Kayla's league, there was mercy rules. And in Cam's league, was there mercy rules for you? Yeah. Except for the final inning.
And mine, there's a mercy rule 5 each inning. Even if you have 0 outs or 1 out, and they score 5, the other team gets to bat.
Did you ever stop a team from scoring 5 runs? How'd you do it?
3 outs.
What did you do?
We got 3 outs.
You got 3 outs. Do you remember how you got the 3rd out?
Yes. I do. Oh.
What did you do?
Was it the home?
You stepped on home plate.
So, we were playing a team, and one of the guys was so exciting that they were scoring.
You want to come up here?
Sure. I do.
No, we'll let Kayla, we'll give you a baseball story later.
This is the base. Watch what they did.
They jumped over the base.
And I saw that they jumped over, and I had the ball. I was the fielding pitcher, and I stepped on the base, and they were out.
Excellent. You can take a munchkin for that.
They would also be out if they went out of the base.
If they went out of the base path as well.
And also,
Yes.
then
You can have a munchkin.
went- and then they went back instead, but it was already too late.
Right. No, you stepped on it multiple times. You got
I
them.
stepped on it too.
Yes. So the lesson from that, which is why I wanted to tell the story, is be careful, check your work. Some of you on the exams did not always answer the question that was asked. The job of that runner was to step on home plate. And that runner thought he stepped on home plate and went off and celebrated, did not check. I was actually thinking at first that you can tell the 3rd base story, but what's another distribution we can use other than the normal that doesn't have the problem of being negative and has low probability of high runs? Well, but Poisson is discrete, so what would be like a exponential? Thank you. Good. There's really natural choices and progressions, so we could try an exponential. But this is, again, not good for baseball because it just doesn't fit the observed data. And this is why you want to take a class like 341. We teach you a lot of these distributions, so when you go to statistics, when you go to these other classes, you actually have a bunch of tools in your chest. All right. So here's a new distribution to look at, the Weibel distribution. You may recognize this from an exam. Okay? It's extremely useful. It has 3 parameters, alpha, beta, and gamma. Alpha, beta, and gamma. Beta basically just translates the whole thing. In basketball, nobody scores fewer than 40 points in the pros. I don't care how bad the team is. So you might want to just translate the whole thing to just start the distribution at 40. Alpha, think of it as converting from meters to feet. It just rescales things. The key parameter here is gamma, which changes the shape. Okay? And so the question is, does a y-able fit baseball data? It turns out to be very nice to work with mathematically, and that's why I gave it to you on an exam. Well, what does it look like? Well, here's a bunch of different plots. The red line is the exponential. So the exponential is actually a special case of the y-able when gamma equals 1. And if you look at it, gamma equals 1 is the value you want to take. What's the second value of gamma you'd want to take? No, I'll tell you one. Another 15 minutes. Careful, Kayla. Thank you. What's the next value for gamma you'd take? 2. And it looks like something like a little tweak of a Gaussian. But what was so painful about integrating a Gaussian? You have e to the minus x squared. You didn't have that x. But in the y-able, you do have the x. So the y-able is going to be very nice for integrating. In fact, for any value of gamma, we can do all the integrals we want in closed form. This is why you want to learn all these different distributions. I had a thesis student a couple of years ago. We looked at linear combinations of y-ables. So instead of doing Taylor series in terms of 1x squared, we actually expanded things in terms of y-ables and did great fitting with that. Y-able occurs a lot of times in survival analysis. If gamma is less than 1, it's high infant mortality. Gamma greater than 1, people survive a lot into old age in terms of just looking at the distributions. So we all remember the gamma function. It's the generalization of the factorial function, e to the minus u to the s minus 1 du. It turns out for the y-able, when you do the integration, you get nice formulas for the mean and the variance in terms of the gamma function. Beautiful closed form expressions. These are the ones from the exam. This was not a cookbook problem. This was a key problem to deal with this analysis. Okay, and this is all on the slide, so you can just enjoy the calculation. If we want to calculate the mean, we basically do a bunch of change of variables, let u equal blah. When we then put this in, we now have an integral here. We do our trick of adding and subtracting 1, or just moving it around, and we notice it's a y-able. We notice it's a gamma function, and we have a nice closed form expression. If you want to calculate the variance, it's a very similar quantity. We can get a closed form expression for that. So here is from, I think, MLB.com. I just chose the random data in 2008. It's coincidental that the Red Sox happen to be in first. And if you look at the data they give wins, losses, winning percentage, games back, last 10 games, winning streak, interleague play, home record, road record, and expected won loss, the Pythagorean prediction. This is expensive real estate on a web page. They do not put stuff there that does not matter. So if they're putting it up, this is something people really care about. And again, if you don't happen to care about baseball, look at this in terms of economics, trying to evaluate different stocks or mutual funds or businesses and figure out which one is undervalued, which one is overvalued. That's all that we're doing here. We're just applying it to baseball. I'm not going to go into this too much. Did we do this on the first day of class, or did I not do that this year? This is a simpler version of trying to come up with a very nice formula for what's the probability team A beats team B if team A wins P% of their games and B wins Q% of their games. I'm going to skip this for now. Okay, but you can hit pause or you can look at the slides online because I did toggle through them. So the Pythagorean one-loss formula, I proved this back when I was a postdoc at Brown, is if the runs scored and allowed are independent y-able random variables with the same gamma and the same beta, and I'm always going to choose beta to be negative a half. And the reason is my bin is going to go from negative a half to 1/2. What's in the middle of that bin?
0.
The next bin is from 1/2 to 1.5. What's in the middle of that bin?
What?
1/2 to 1.5. What's in the middle?
1.
1.5 to 2.5. What's in the middle?
0.
So if you choose beta to be a negative a half, all of your scores are right in the middle of the bin. If you choose your bin to be from 0 to 1, 1 to 2, 2 to 3, then your scores are right at the end point. And when you're trying to decide where to put things, it's very bad. So even though baseball is discrete, if we just translate by negative a half, it actually smooths things out a lot. It makes the mathematics much easier if the gamma is the same for the two teams. And then they have different alphas, and that reflects their propensity to score runs or to allow runs. And so let's go through the proof very quickly. So x and y are independent random y-ables. These are their parameters. They have means rs minus beta and ra minus beta, And this gives us the values of the alphas for the runs scored and the runs allowed Weibel. And now we want to just calculate the probability x is greater than y. Which class teaches us how to do this? Nope, not probability. What class teaches us how to calculate the probability that x is greater than y? I'm sorry? Not Calc 2, a little bit more than Calc 2. Calc 3, because it's going to be a double integral, right? We want to calculate the probability x is greater than y, so we have our two densities, and we just want to find the area where x goes from beta to infinity, y goes from beta to x. So we substitute in, and it's just worth seeing how to do the algebra in a nice way. So we do the y integral, we do the change of variables, and when we do the change of variables, u equals this. I've shifted the betas to be 0, and we get this really nice expression. What is the x integral times the 1 dx? What does that equal? It's a Weibel, and we integrate over the whole region. That's why that first part is 1. The second part is we have this times this crap over here. So we have to combine the exponentials. And so they both have an e to the negative x to the gamma. This one is divided by alpha rs to the gamma. This is alpha ra to the gamma. I can call that the sum of those reciprocals 1 over alpha to the gamma. And it now looks almost like a new Weibel with parameter alpha. So all I would have to do is change this by multiplying by 1 in a clever way. Has anybody seen a formula like this before? Hopefully you've seen this formula before. I'm sorry? Similar to partial fractions, but it's in physics where you see combinations like this. Resistors in, I always forget if it's parallel or it's in parallel. This is how you combine two resistors in parallel to find the net resistance. Also in some center of mass problems for physics when you have two bodies. This idea of combining things is a very good idea in terms of dealing with algebra. And it allows us to look at this as a new Weibel that we can understand, and this gives us an effective alpha from the two of them. So this is an idea which you've hopefully seen in some other classes. Well, now we just continue. We multiply by 1. It's one of the only things I can do. The integral now becomes 1, and we have the stuff outside. We then just simplify the denominators, and at the end of the day, we substitute in, and there's our formula. So if I had to choose a baseball season to analyze, what season should I do? 04, absolutely. Now it says here, I'm a Red Sox fan. This changed my life. You know what that is, Kayla? Who's the pitcher? Do you remember the pitcher's name? Who's the pitcher? Kurt Schilling. Okay. So we'll just do 2004. So here is the predicted best fit Weibels. I'm using the method of maximum likelihood. You'll hopefully learn that in a stats class. Good fit or bad fit? Or okay fit? Okay fit's allowed. So I'm hearing good to okay. I'm definitely seeing we want a better way of judging how good a fit is than just eyeball inspection. All right, let's do a little bit of data as to what we're doing. We're going to use the method of least squares, one of my favorite techniques, one of my favorite subjects to do in my classes. So bin k is the kth bin. RS observed k is the observed number of games where we score whatever is in that kth bin. Alpha gamma k is the area under the Weibel in bin k. And we want to find the best fit values that minimize the sum of the squares of the errors. And so again, here's the Red Sox, New York Yankees. What do you think? Good fit, bad fit, okay fit? Good fit? Baltimore Orioles. I don't think it's quite as good of a fit as the Yankees, but Tampa Bay Devil Rays, and they were the Devil Rays back then. They may not have been good at winning games, but in terms of having the right decay, they were phenomenal. Sadly, there's not that much reward in baseball for decaying in your run production. Toronto Blue Jays. Good fit, bad fit? I think this is the worst of all the fits we've seen. But what do you have to remember about the Toronto Blue Jays? They're in Canada. Okay, this has absolutely nothing to do with them being a Canadian team. This is not from the metric versus the English. They don't have metric runs in Canada. Okay, and I'll show you later that it's actually good that the data for Toronto is not perfect. So here's a little bit of advanced theory. So if you have some free time later today, I urge you to flip a fair coin 1,000,000 times and record the results. All right, we expect about 500,000 heads. Anybody want to tell me approximately what the scale of fluctuation should be? On what order? 10, 100, 1,000, 10,000, 100,000. On what order? Why 10,000? Roughly, if we flip something n times, what should the error of the fluctuations be about? Square root of n. So what's square root of 1,000,000? 1,000. It's probably a reason I chose a nice number like that. You expect fluctuations on the order of 1,000. So 95% of the time, it turns out we should be between 499,000 and 501,000. And we also have the square root of 1/2, 1 minus 1/2. Imagine we flip n. We have n teams, and each team is going to flip 1,000,000 coins and see if they're outside this range. Now, 95% of the time you should be in this range, but if we have 5 teams, the probability that one of the 5 teams is outside the range is 22%. With 14 teams, which is how many teams were in the American League back then, it's 51%. With 50 teams, there's a 92% chance that at least one team will be outside. So with the 14 teams, I've got a 50% chance that at least one team should not be a good fit. So if I'm not cooking the data, if the data looks too good, you should be suspicious. Do not trust people just because they give you data. I'm not saying I forged this data, but at least passes that test. So if you look, it turns out you can do this goodness of fit test using chi-squared. And this is going back to sums of normal. What's the sum of a normal random variable? Chi-squared. And if all the errors are independent, sums of chi-squareds become chi-squareds. So these would be chi-squareds. If I'm doing runs scored and runs allowed, the y-values, that's 20 degrees of freedom. If I'm doing whether or not runs scored and runs allowed are independent, that's 109 degrees of freedom. I'm not going to get into that test right now. According to theory, about 95% of the time, I should have at most 31.4. 99% of the time, I should be at most 37.5. And if you look, all the numbers are really good except for who? The Blue Jays. But if you do some advanced theory, how many of you have heard of Bonferroni adjustment? Excellent. For those of you who continue in statistics, you can now say you heard it here first. What Bonferroni adjustment says is, if you're trying to decide if these multiple comparisons are good, you have to take into account that the more comparisons you do, the more likely it is that at least one of them will be outside your confidence window through no fault of the theory being wrong, just because you're doing so many comparisons. If I were to do the comparisons 100 times, how often do you think I should be outside the 95% band? 5 times. So the more times you do the comparisons, the more likely it is that you're outside. So there's a way to adjust these things. It's called the Bonferroni adjustment. And the new value becomes 41.14 at the 95% level. And if you look at the Blue Jays, 41.18, that's essentially right where it should be. Just want to talk briefly about structural zeros. This is what I was telling you before with these R by C contingency tables. All right, Kayla, if you want to come here now, you can, because it's the last 5 minutes. Well, let's let Kayla do it. You're doing such a good job, Cam. I will remember this. Okay? All right? You can have a munchkin, because Kayla's sitting with me. Okay?
We had a munchkin at the beginning.
I know. Okay, so we have, you can have one more later, okay? Munchkins are good. Okay, so wait. Okay, you can have your munchkin now, but we're going to finish the lecture. We're almost done. So these are called structural zeros. Okay, can you stay on the side? Can you hit page down when I tell you to? Okay, not yet. So hit page down now. Oh, okay. Oh, okay, hit page up. Okay, so I guess that's all I chose to put in here. The rest is in the appendices. It's to deal with these issues. Don't fight. Okay, it's to deal with these issues when you are not allowed to have certain events happen. When you're not allowed to have runs scored and runs allowed be equal, how do you do these tests? So for those of you who want to know, it's in the appendices. Okay, you want to now hit page down. Summary, page down again. All right, so this is the data using the method of maximum likelihood. The last column is the best fit values of gamma. All right, Kayla. It's got to be on me because I'm recording. You've got to be quiet so I can finish, or you have to go back to your seat. All right. So look at the values of the best fit values of gamma. For the 14 teams, I get a mean value of 1.74, standard deviation 0.06, median 1.76. This is pretty close to the numerically observed value of 1.82. The way they got the value of 1.82 is they assumed the Pythagorean formula worked, and oops, go back. They assumed the value worked, and then they just went through all the different exponents to see which exponent gave the best value. What I did is I chose a model for how runs are scored and allowed to simulate a baseball game, and then found the best fit values of gamma by using the actual baseball data. This is a very simple model. It has issues, but it does a really good job. It's very simple, and it gives you some theoretical justification for using the Pythagorean formula. Or Kayla, you can let Kayla hit page down now. Hit page, this one here, hit page down. So, stop Kim. Okay, we're going to stop here. So the conclusions, we can find parameters such that the y-ball is a good fit. The runs scored and allowed per game are statistically independent. Does that mean the same as they're independent? All right, stop shaking, guys. Is that the same as they're independent? No, we know they're not independent, but they seem to behave as if they're independent given that they cannot be equal. The Pythagorean one-loss formula is now a consequence of our model. Our best fit value is pretty close. Okay, it's Cam's turn to hit, it's Cam's turn, you get the next one. Oops, go back one. Nope, you get to do the next one. So here's some other stuff you can do. You can do a microanalysis. You can take into account, big leads, close games. Anybody remember the 2000 presidential election? What did the news networks do incorrectly?
They announced too early.
Which state did they announce too early? They called Florida while the polls were still open. They forgot that the Florida Panhandle is in a different time zone. The Florida Panhandle is a heavily Republican country. What happened to a lot of people in the Panhandle when they heard Florida called for Al Gore? I'm sorry? Nope, they did the opposite. They left the lines. When they heard Florida was called for Gore, a lot of people, they estimate 10,000 people in the Panhandle, went home. Should they be allowed to re-vote? No, they chose to go home. They chose to listen to the news. You've got to be very careful when you're doing your analysis. You don't want to conclude something too early. Now, when the voting is still going on, it's bad in a very close race to make predictions. It's very dangerous. It can lead to a lot of consequences. In this, they were too close to really make the call at that point. They had forgotten that more votes were coming in the Panhandle. You can try to do this in other sports and see how gamma changes and see how good it does. Which sport do you think it's going to be the worst at? Football. Fewest games. And if you have a really good record, you often don't care about your final few games. Another big issue is closed forms. Are there other probability distributions that will lead to closed form answers that do a better job? It also gives us some work in valuing runs. Right now, the typical analysis is every 10 runs you either score or save is worth 1 win. And this helps you do a more refined analysis. Okay, Kayla, hit page down. So, smoots. So I'm going to do the rest here. Okay, Kim and Kayla, you need to return to your seats now. Thank you. Nope, nope. No, Kayla can get one because she didn't have it at the start. So I said at the beginning of the, to seize opportunity. No, Kim, don't. Sit down. Sit down. So I said seize opportunities. You never know where they will lead to. All right, you'll get other things today. Anybody know what happened to Smoot? Nope. Close though. So this is Smoot after college many years later, chairman of the American National Standards Institute. So the person who was used as a measuring stick became the chairman of the American National Standards Institute and president of the International Organization for Standardization. You cannot make this stuff up. All right, and so just very quickly, here are the references so that people can pause if they're watching at home. Appendices, I'm just going through the calculations very fast. This is how to deal with structural zeros. This is the central limit theorem, which you've all seen many times. And this is just so it's now, you can take your notebook. All right, so that's it for the class. We will do more advanced lectures of applications on Wednesday.
For lunch.
It is time for lunch.